Okay, micro's okay?
Yes.
Okay. So I was stating a few theorems. So this one here is due to Wang. And then let's call it condition C. If in addition V mod is semi-simple, then this V mod is in fact a semi-simple modular tensor category. Is a modular tensor category, and remember in the last lecture I worked out this Verlinde formula for modular tensor categories. So in effect, statement C here is also due to Wang. And moreover, in this case, the following so last lecture I told you one can use the Hopf link to derive this Verlinde formula. And what Wang also proved is and the following nice identity holds. I'll explain the symbols in a moment. So this Hopf link S is exactly the one I introduced for tensor categories that have a trace. So this is supposed to be a Hopf link here. This one, a little bit funny. And what is this S chi? This chi is defined via the following. I introduced the character of a module exactly in the same way I have introduced this earlier for Fock modules. So these characters are graded by conformal weight, and so you can take a graded trace. That's the Q series. It converges for Q in the upper half plane. So you write Q as e to the 2 for Q absolute value less than 1. And so you can write Q as e to the 2 pi I tau, tau on the upper half plane. SL2Z acts on the upper half plane. So I can write down the S transformation, everything very much as in last lecture. And so I can write this. And another theorem, this one here is actually due to Zhu. You don't pronounce it this way, I just can't pronounce the name, I'm sorry. This is so very much like in the example I presented in the Heisenberg case, the S transformation replacing tau by -1 over tau is a linear combination of characters. Here it's a true linear combination because C2 cofiniteness turns out implies already that this category here is a finite tensor category. It doesn't imply that it is semi-simple. This statement, if we go back to the categorical statement,
what does it mean that it's finite?
Finitely many inequivalent simple objects. So this means that in particular this is a finite sum. The set here is finite.
SAB chi is something you haven't defined. Is SAB chi something you have not defined?
This is the definition of S. This is the definition of it. So it's a theorem that and this is due to a 96 or so paper by Zhu, that if the C2 cofiniteness condition together with the semi-simplicity hold, if all these holds, then any character, in fact, any character is a linear combination of characters. If you do S transformation and the coefficients, they are the definition of this S. Very much how we the deep theorem is this equality, which then immediately implies that actually also not only the categorical S transformation, but also the modular S transformation gives you a formula for the fusion rules. That's kind of nice because these fusion rules are hard to get. Modular transformations are much, much simpler to compute. These are something you can, one of the first things you can compute. Okay. Now it turns out until a long, for a long while.
While you were erasing that, did you do your homework over the break? And
No, I didn't because of all the questions. I'm sorry. I didn't know. Okay, now you can, for a long while, the whole theory was focused on this case. It's called the rational case because it corresponds to rational conformal field theory, what physics has always been interested in. And let me just say in a few words what are. There are a bunch of known vertex algebras that satisfy those rationality properties. So for affine vertex algebras, it's the simple affine vertex algebra at level k if and only if this level is a non-negative integer. So this is what one usually calls the Wessel-Witten cases. And then it turns out, for example, the Virasoro algebra.
I think it would be good if you wrote what you were saying.
Okay. So this case here, C is called rational or strongly rational. And we have the statement that an affine vertex algebra is rational if and only if this level is a non-negative integer.
Can you just recall what is this algebra?
It's the simple quotient of the universal affine vertex algebra. So we had this 2 or 3 days ago at some point. Yeah. So this is the reminder, right? I always defined the universal one. And now it can happen that the universal one as a G-hat module is not simple. It has an ideal. And then you can take the quotient by its maximal ideal. It has a unique maximal ideal. The quotient inherits a vertex algebra structure. It's called the simple affine vertex algebra, denoted by the symbol L. A quotient of a vertex algebra always has much, much fewer modules. And it turns out if this level is an integer, a positive non-negative integer, the ideal is particular big, so you quotient by particularly a lot, and so that's why you get this rationality. In general, rationality is a rare thing, so then there's another series called minimal models, of course, but I haven't talked about these types of algebras. I want to do that tomorrow, so why don't I not say anything more about that? It turns out it has taken a very, very long time to find a vertex algebra that satisfies condition B, but not in addition condition C. And so for a long while, people believed that already B implies C. So this rationality is automatically. That's totally false. So it's and there are surely more VOAs that satisfy only B than both B and C. I mean that satisfy B but not C than the rational ones. But the first example people understood are these symplectic fermions. It's in fact a superalgebra. And then the next one understood are the so-called triplet algebras, which if you read work about the relation to 3 manifolds all the time appear there. But the state of the art is really that one has, except for those triplet algebras, no further such examples that are not rational. And that's very sad because these types of vertex algebras are the ones, as a physicist, you want to understand, probably also as a topologist, they are really interesting. And so it's something one wants to do, is one wants to understand more examples. Well, finding more potential examples is not hard. The problem is you always have a hard time to prove this condition. So it's one of the technical issues of the area presently. I can't, but you can. Can you try, please? Yeah, I think you have. That might also be because I'm getting tired. I'm really losing a little bit my energy. So that's waking me up. So the problem is if it's too much, it's an echo, right? Okay. Yeah. Okay, and from a practical purpose, so I didn't mention C1 cofiniteness, but C1 cofiniteness is the thing that guarantees closure under tensor product, and it also guarantees existence of differential equations. So this means, in particular, this here, this last one is the practical one. So if we have a category of V modules, it doesn't need to be the full category of all modules, such that every object in this category is C1 cofinite. This category is abelian. So the quotient of a C1 cofinite module is always C1 cofinite, but a submodule of a C1 cofinite module needs not to be a C1 cofinite. That's why you have to put this here as an extra condition. Then it needs to be closed under contragradient dual. And it's an open conjecture that the contragradient dual of a C1 cofinite module is also C1 cofinite. So that means in this setting it's an open conjecture that one can remove this line. And also closed under tensor product. Then it follows that C is a vertex tensor category. So in particular, if I take the category of all C1 cofinite modules, then the closure of under tensor product is automatic. Then I don't need this condition anymore, right? But I still have to understand that submodules are also C1 cofinite, and I still have to understand the closure under contragradient dual. But these are things that are fairly accessible, so this is a good criterion. And but now we go back to the drawback again. This is what I ended last lecture with. I told you what are exactly the C1 cofinite modules of an affine vertex algebra that are exactly those modules that have finite dimensional top level. And already in the example of SL2, we saw that that is rare. So, yeah.
So, why can you now not say MTC? Because now you have duals. Whereas before
Under contragradient dual, that's not the dual in the categorical sense. If the category has a duality, then the dual module needs to be the contragradient dual, but the category does not need to have duality.
Okay, thank you.
Right, that's a very good comment. So this only guarantees that it is a vertex tensor category. If you go through the list, duality is missing. So duality is not guaranteed by any theorem. But conjecturally, you can almost always prove duality if you're very good. I mean, vertex tensor categories should usually have duality. Okay. Now, I wanted to give you a summary what one knows about tensor categories of affine vertex algebras, and then ideally also give you more information what we know about SL2, but time will be an issue, and I'm wondering whether you want me to continue tomorrow with categorical statements, or if you prefer that I say more about W algebras and cosets, which was originally announced. So why can't any one of you who wants me to continue with categorical things raise her hand now, and the other?
I don't understand what are these two different possibilities.
So, my lectures have totally focused on representation theory, and that's something very interesting in vertex algebras. But I also haven't given you many examples, and all I have said at the beginning is that every vertex algebra somehow comes from an affine vertex algebra. Now, the standard construction is the construction of W algebras from affine vertex algebras. And another standard construction is the coset construction. It would be appropriate to lose a few words or a few hours on that. Shall I do that tomorrow?
Yes, please.
Okay, so then that's agreement.
What was the other option? What was the other option?
To continue with categorical things.
And we want to see a log.
You want to see a log? Yeah.
Do a log conformal, whatever. Something. Maybe we won't get.
Yeah. Everybody wants something, right? Yeah.
Once upon a time, one of these options was this new business but SL2, right?
Yeah, and now it turns out for the new business of SL2, it's quite interesting and quite exciting and tricky. And so I got the invitation to give an 8-lecture series on that in a month, and it will be completely recorded. So I thought, why don't I spend 8 lectures on it and send you all the link, and you can look into it if you like it, and if you're not interested in it, you don't look at it. So that would be an option, right? And yeah, anyway. Yeah, that will be completely online. It's but anyway. So I want to talk about categories of affine vertex algebra. So of the universal one first, and then of the simple quotient. And so it turns out the thing you would like to do is you want to introduce a sequence of 4 categories. First a big one, and then 3 smaller ones that are the interesting categories of modules. So let me say what these are. These are the big category. We want to have finitely generated smooth weight modules at level k with finite dimensional weight spaces. So this means we would like a module to be of the type it is bi-graded by the Cartan subalgebra of the Lie algebra and by L0 eigenvalue. You require that these bi-graded spaces are finite dimensional. This is something that fails already for SL3 in whole generality, so there are modules that don't satisfy this property. Well, finitely generated is clear. Smooth, so weight means this condition. Smooth means that for every x in the Lie algebra, there exists a sufficiently positive integer such, for any element in the Lie algebra and any vector on the module, there exists a sufficiently positive integer such that xn annihilates that vector. Level k is clear and finite dimensional, I said. Okay.
Lambda is now a weight?
It's a weight with respect to the Cartan subalgebra of G.
And the delta is for the action of the Calvin?
It's for the action. So this is L0, and this is Cartan subalgebra. Cartan subalgebra. Okay, and now we want to have a subcategory where in addition we want the conformal weight to be lower bounded. And this is the category you understand in the sense that every module here is comes from a module of the finite dimensional Lie algebra. All right, this is what the lower boundedness condition means. So these are the ones you probably feel most comfortable with, or maybe of course there are subcategories. And now we can define two more categories with an additional index O and an index Kashtan-Lustig. And here the condition is that each weight eigenspace is in the category O, is the highest weight module, and here we even require that each conformal weight eigenspace is finite dimensional. Now, from the C1 cofiniteness problem before, we had a module is C1 cofinite precisely if it's a module in here. And in fact, in the 90s, K and L, Kashtan and Lustig wrote a series of 4 very influential papers where they showed that on this category here you have a tensor category, a braided tensor category, and moreover this braided tensor category has duality and is equivalent to the category of the corresponding quantum group where the Q parameter depends on the level in a certain way. So that was a really nice theorem. The existence of the tensor category follows immediately from this criterion. So it's a nice example of that one. Okay. These the category O, so this means that the highest weight modules with respect to the action of G. Okay, and now I also introduce the categories LKG with a corresponding LKG weight mod with a corresponding label, and these are the corresponding modules of VKG in these 4 categories. So these are the objects in the corresponding category of the universal affine VUA that are also modules for the simple VOA. These will be subcategories of these 4 categories with an additional property that you can give a module structure for this vertex algebra on it. So, okay, let me tell you what is known. Well, and then you see it's not that means if you are interested in an area where there are many interesting things to discover, this is a good area. So we are interested in K being admissible. Let me write down what this precisely means. So that means that K, the level plus the dual Coxeter number, is a rational number. We write it as U over V. It needs to be a positive rational number. So, and one has the condition on the numerator. The numerator has to be at least the dual Coxeter number if V is co-prime to the laicity of G. So this R is the laicity. and it has to be at least the Coxeter number if V is a multiple of the laicity. So the laicity of type ADE is 1, B, C, F is 2, and G is 3. Just and H check and H dual Coxeter and Coxeter number are certain invariants. So remember, I stated at some point that VKG and its simple quotients, they do coincide, except if K plus H check is a positive rational number, and you see, and a level is now called admissible if K plus H check is a positive rational number that is not too small in this sense. Right? So it's and you see this in some sense. This covers almost all such ones. From the representation theory point of view, it turns out those that satisfy this positivity conditions and are not admissible are extremely difficult to get a hand on, but also they seem to be really, really interesting. So it's something one definitely wants to study, but somehow we always get only families of them, example by example, but at least families of examples. Anyway, so what kind of properties are known about this category? So and now I start with the smallest one, the Kashtan-Lusztig category. So, and this category is known to be semi-simple. This is a theorem by Arakawa. Then it is a braided tensor category, which follows directly from the criterion D that I wrote down. And by the way, this criterion D is a paper with my, at that time, postdoc Jinwei Yang and myself. So that was really useful. This category is rigid, so we have duality, but in type ADE, in the simply laced type. So it turns out that was it was a consequence of a Coset theorem that I will probably present tomorrow. It was a really nice consequence. And what it turns out is, what is really nice is all above also holds for a Lie superalgebra, namely for the Lie superalgebra OSP 1/2n. So there's one single family of Lie superalgebras that behaves very much like a simple Lie algebra. It's this OSP 1/2n. The main thing of it is it has a unique invariant bilinear form that is positive definite. So for a superalgebra, the bilinear form is always a supertrace. So you have a hard problem to make it definite. It turns out only on OSP 1/2n you can do it, and that's the key thing for this to behave in the same way. So we have proven this statement fairly recently. Okay, now, and I want to just continue by giving you a list about what is known about this category. So the category O is a little bit bigger, and for that category we still have semi-simplicity. That is the same proof as, Arakawa proved this one, so that's, and since this is a subcategory that holds for this one as well. What else is known? There's a really nice statement that the characters, graded characters are nice in the sense that they can be meromorphically continued. So they are continued to meromorphic Jacobi forms. So this to vector valued meromorphic Jacobi forms. So this in particular the space of characters inherits its meromorphic continuation has an SL2Z action. So you can play the Verlinde formula game. And it turns out Linde's formula doesn't make sense. It's inconsistent. So, but in a somehow mild way, you use this formula, NABC is equal to the sum of S matrix elements, and you observe you always get an integer, but sometimes this integer is negative, and a negative integer has a hard time to be a dimension. And one more thing that turns out, this category is not closed under fusion, under tensor product. So already in SL2 you find a counterexample. And right. And then let me go on. What about the other, the larger categories? What about the lower bounded modules? There we have one single statement. Simple modules are classified. This is a maybe 3-year-old result by Cosets and Redoubt. And in general, one has the following statement. Every module, every simple module in the big category is a spectral flow image of one in the category of lower bounded modules. So this is a 20-year-old result by Futoni and Silke. So let's digest this statement, and let me please just say it in words. So this spectral flow, Gabriele nicely asked me yesterday the question when we discussed delta operator and spectral flow, how does it relate to affine vertex algebras? And then I explained in that example of SL2 that the spectral flow automorphisms are precisely the ones that come from affine Weil translations. So this means for every element of the covariant lattice we have an automorphism. This automorphism of the Lie algebra doesn't leave the embedding of the horizontal subalgebra invariant. And so in particular it does not leave this category invariant. It maps it to a translated category, a category that has this lower boundedness condition with respect to a different embedding of the horizontal subalgebra. And it turns out this classification result by Cosets and Redoubt is good enough because on the level of simple modules, this is all. However, it turns out that extensions you have, so this means, this tells you on the level of simple modules, the big category is graded by the covariant lattice. And now what's the problem? The problem is you have many non-trivial extensions between different blocks, and they are quite hard to get. And now, now I don't have much time. So now I wanted to explain a little bit more on SL2. Well, actually, I'll not write everything. I think then I can get quite far. So, so, yeah.
Is that category proof that semi-simple?
Yeah, and the category is totally not semi-simple. Otherwise, I would be done here. Right, good question. So we are very far away from being done because these categories are not semi-simple, and so that means the main question one has to ask at this moment is, can I construct extensions between different modules, and can I find all of them in a certain sense? And this is quite hard because every problem is difficult because the standard Lie theory for these extensions, because it's extensions between different of the spectral flow blocks, you don't have yet a good technology. Anyway, let me give you an example of an extension. So let me give you an example of such an extension. And so the sigma L denotes the spectral flow twist by L. I wrote down the formula for that when I discussed the delta operator. And then I have here the module of the affine vertex algebra, the highest weight module with a certain weight label, R, S. For the discussion here now, it's not important what this number is. It's a certain number that depends on R and S and the level. And it turns out this module has an extension. This lives in the spectral flow orbit number L to the L plus 1. Where the labels change a little bit. And it also it's quite symmetric in the sense that there's also an extension in the other spectral flow direction. Also the weight label changes in a different way. And okay, so and this is exactly the type of Löwy diagram that I wrote down for the symplectic fermions, right? The symplectic fermions, this VOA, they had a four-dimensional module, which, I mean, not four-dimensional, a module that had 4 composition factors. It was generated, it had the symplectic fermion as submodule. It had 2 copies of them as quotient, and then if you quotient again, you get 1 more. And it turns out for SL2 at admissible level, the projective modules, so it turns out these modules are all projective and injective, have the same type of Löwy diagram as in the symplectic fermion case, and nothing more complicated. So in fact, the extension structure is uniform and fairly nice. It's the same type of extension structure that you get in for the unrolled small quantum group, so for those who know what that is. And the theorem that we have, Kawasetsu, Arakawa, and myself, is that these projective modules, together with the simple projective modules that we already know, which is a huge list, are a complete list of projective modules. So this means, let me write this down as for SL2 level being admissible, exactly like here, there's a classification of projective modules, projective and injective modules. And the category of modules is generically semi-simple, meaning the generic projective module is a simple module, but you also have these kind of nice ones. Okay, and now you also would like to get a tensor category. And the statement is that the big category is a vertex tensor category. Okay. How do you prove this? Well, the only good criterion is criterion D, I wrote down, and it uses C1 cofiniteness, and only the category Kashtan-Lustig is C1 cofinite. So, and this is a super small subcategory of this big thing. So how can I possibly do that? Well, this is done as follows. It turns out, next lecture I will come to W algebras and coset, and it turns out that SL2 enjoys a very nice relation. It's called Kazama-Suzuki coset construction to the n equals 2 super Virasoro algebra. If one understands these relations good enough, one can prove that this category here has a vertex tensor category structure if and only if the superalgebra has one. In the superalgebras, you see this cofiniteness condition is about a statement about relations and modules. And relations you get when you have nilpotent operators, right? If you have a nilpotent operator, you have a super nice relation. That's as good as it can get. Well, the odd elements, in particular of the super Virasoro algebra, they do square to 0. So this means you get an enormous amount of relations. And it turns out, while the category of C1 cofinite modules here is super small, on the super side, it is everything. And that means the existence of the vertex tensor category is trivial. Right? And I really like this because I will stop for today. I will stop for categories, and tomorrow I will talk about W algebras, and what I know it will be sketchy because it's only 4 hours. But the upshot here is there's another area in VOAs that seems to be completely unrelated to the representation theory, and this is called, one likes to call it correspondences, trialities, duality, whatever, somehow surprising isomorphisms between seemingly unrelated vertex algebras, motivated, of course, from physics. And it turns out one can they become all of a sudden enormously useful because you have 2 algebras that are somehow related, and I will come to that tomorrow, what somehow related means. One of them is maybe accessible to Lie theory in some sense, so SL2 is something just we know by heart. And I probably, we could prove this statement so well just because we knew SL2 by heart. It was, because of this were technical, tedious computations, it's just that, so this means we were able to do classification on the SL2 side. Maybe we would also have been able to do it on the super side, but I actually imagine it would have been substantially harder. So we could do some kind of representation theory on the abelian level, on the VOA side, and then there is a dual superalgebra, and the superalgebra enjoys nicer finiteness condition that allows to get existence result. So that means all of a sudden the dualities are not just interesting because of the relation to physics and other areas, but they are also interesting because they give substantial structural results on the representation theory. Very good. Any questions? So yeah, I'm sure this was quite quick, but I will. So if you're interested in this, I will send you the link or announcement to the lectures, and they will be recorded, so you can fast forward, right? And time zone will be good for a few. So we have many participants from South Korea, so for those the time zone will be good. For others it won't be that good. Yeah. Good.